everyone. My name's Godfrey. I'm a network supervisor for Cadent Pipelines in the Northwest Department. And today I'm going to talk to you about cathodic protection. So there's the agenda. I'm going to tell you what CP is, talk a little bit about compliance and how the HSE are interested in cathodic protection, and then move on to the factors that affect the cathodic protection on our networks. So if you were to Google cathodic protection, you'd get a definition that looks something like that. But essentially what cathodic protection is a system that we utilize to prevent corrosion of our steel pipelines of all pressure ranges. It's not just employed by Cadent, it's used in all gas and oil industries and even the water industry. Cathodic protection, although it's used to prevent corrosion, it is merely a secondary method of protection. Our primary method of protection is the pipeline coating. So as many of you are probably thinking, if you've got your pipelines coated, then where's the requirement for cathodic protection? Well, no matter how well a pipeline is coated, there's always going to be deficiencies in it somewhere along the line, whether it be at the valves or flanges or anywhere that's awkward to coat or apply a decent wrap to the pipe. So that's where cathodic protection comes into play. At these small locations and defects in the coatings is where the CP will protect the pipe from corrosion. There's a little bit of theory of where the steel comes from. The steel is mined in iron and comes out in the form of iron ore and goes through foundries and various processes to eventually result in the steel that we see and recognize today, whether it be in cars or in our pipelines. But the steel will always try to return back to its original form, and it does so in the form of rust, which is hydrated iron oxide. There are 4 requisites for this corrosion to occur. You need an anode, a cathode, electrolyte, and a metallic connection. So those are the anodes. The anodes are essentially what we sacrifice to protect our pipelines. You can see the anode bags in the excavation on the left-hand side there, and also the picture on the right shows a new anode rod and an old anode rod out of a heater element, so you can see the effect corrosion will have on these sacrificial anodes. The cathode is what we're trying to protect. In the picture there, in the center of the picture, you'll see a yellow pipeline running through the middle, which may look like a plastic pipe to some of you, but that is in fact one of our intermediate pressure pipelines with a plastic polyethylene coating. So the cathode is what we're trying to protect. We sacrifice the anodes to protect the cathodes. For the electrochemical process to operate, you need an electrolyte. Both the anodes and the cathode need to be submerged within the same electrolyte. This electrolyte has to have oxygen and moisture to allow the current to flow. So you can see an excavation there with our pipe in the middle of it. And in that case, the soil is the electrolyte. The one on the right-hand side, obviously, the soil is the water surrounding the pipe. You need a metallic connection. You have to complete the circuit. And this metallic connection is provided via what we employ pin brazers, where we'll connect onto the pipeline. As you can see on the left-hand side, this wire will then run through the soil into the ground and up into a test post, where there'll be more wires that also run down to the anodes. And within the test post is where this connection occurs, and thus completing the circuit. So when you immerse a metal in an electrolyte, it develops a potential. The potential is basically the driving voltage that metal has. And over years, this has been put into a table, and it is known as the galvanic series. So if you just have a look at the top of the table there, commercially pure magnesium has a driving voltage of minus 1.75 volts. And with it having the highest driving voltage, that is what we tend to use for our sacrificial anodes. Midway down the table, you'll see steel, which is what our pipelines are constructed using. And just below that, it's pertinent to note you have cast iron, which will come to light the relevance as we move through this presentation. So when we connect the magnesium up to the steel, the driving voltage is what forces the current through the soil to protect the structure we're trying to protect. That's in our sacrificial anode systems. We also have impressed current systems where we may use a lower graded metal on the scale, where we typically employ silicon iron rods. Now they don't have a driving voltage, as you can see, that will be in contrast to the mild steel that our pipelines are constructed of. And so in those cases, we will impress an electric current which will increase their driving voltage, and this can be utilized for our long-distance rural pipelines. So that's a cross-section of a sacrificial anode bag. Has a magnesium core down the middle, and a powder around the outside called gypsum bentonite, which helps to accentuate the current flow out of the anode into the soil and onto our pipelines. So when you connect the two together, this is what happens. Metal 2 on the right-hand side will become less negative, so that is in effect our anodes. And metal 1 on the left-hand side, which is our steel pipelines, starting off at minus 500 millivolts, will become more negative. And so that's the reaction that occurs. And basically, when that reaction occurs, we will soon be able to tell if our pipelines are protected by the change in potentials. This is a cross-section of how the connection is made. You have the anodes on the right-hand side, cable going up into the test post, and down onto the pipeline, and the current flows through the soil onto the pipeline. So this is how we know if our pipelines are protected. There's a protection criteria applied to them. What we're trying to achieve at these test posts is a reading of minus 1250 millivolts. When we see that, we know that the pipeline is adequately protected, as it has been researched over a number of years. However, that reading has an error in it. The error is caused by the distance between the pipe and the top of the soil, and it's known as a IR error. So to achieve the optimal level of protection, what we need to be aiming for is minus 850 millivolts, but this is at the instant that the current is switched off. So at every test post, our technicians can go along and disconnect the cables, take a reading, and if it's more negative than 850 millivolts, we're protecting our pipelines adequately. So this is where the HSE are interested. Back in 2015, National Grid, as we were then, was served an improvement notice for not adequately protecting their pipelines. And this improvement notice has obviously followed through as we've become cadent and split off. So that's where the medium and low pressure remediation project originated from. So we've employed this project, totaling significant investment of approximately £10.5 million, recruited more staff, engaged new contractors, new designers, and we've also engaged a contractor to map out our systems to display on a Google Earth style application where all our medium and low pressure CP systems are. That graph there depicts the improvement we've made. The improvement notice was served around halfway along that graph, so as you can see, it was recognised long before the HSE took an interest that we had an issue, and improvements and processes were put into place. That's the networks, with different colours shown on a graph, showing our improvement from May 2018. The Northwest network is the light blue line there. And so you can see the improvement up until about the middle of the graph, and then on the right-hand side of the graph, it's showing our projected increase in compliance if we're to continue working at the same capacity that we currently work now. The high and intermediate pressure compliance, although the HSE may not be quite as keen and scrutinising it at the moment, there was also an improvement notice served historically, and hence you can see the improvements that were made in high and intermediate pressure compliance. That's each network. The green line, is the Northwest network. So you can see the improvements we've made over the last, up until April 2018 in that graph, going from around 72% up to close to 90%. And that is the projected change going forward if we're to continue working at the same pace. The pale blue line is the Northwest network again. So we've come across a number of challenges in trying to achieve an increase in compliance. First being contractor issues. Our contracts and procurement team engaged one contractor to design new CP systems and implement the workforce across all 5 cadent networks originally, but however this failed. The contractor were too small and spread too thin and weren't delivering. So in the Northwest we decided to take control of the project and do the design ourselves and use our own original contractors that we had used for the high and intermediate pressure project all along. Another challenge we've had is data errors. Our mains replacement colleagues would come along and replace steel pipelines, insert plastic sections, and split CP systems up, but not inform that there was no communication between departments. So this was showing as non-compliant test posts in every survey because our technicians would go along, take readings, and they'd be reading posts that weren't connected to steel anymore, so they'd be getting less than adequate readings. However, there was no visibility of that, so it just made us look a lot worse than it was. So as part of the project, there's been a massive data cleanse, which has been achieved some good results and helped with the compliance as well as the actual physical work. Lastly, we've had issues with isolation. That's what I'm going to go on to talk about now. So each CP scheme has to be isolated from other structures. As you were looking at the galvanic series earlier on, you'll have seen steel is higher up the scale than iron. We also have a lot of iron pipe, so we need isolation between our steel pipes and our iron pipes. If you don't have the isolation, then the steel will corrode and will in effect become a sacrificial anode for the cast iron. So one of our major issues has been isolation. We're supposed to have isolation joints every area where we've got a change in material. That's a cross-section of an isolation joint there. You've got the pipeline on either side with an insulating material in between. Those are some images displaying what they look like out on site. In our medium and low pressure networks, we tend to have a lot of insulation flanges. Now these flanges should be above ground, but unfortunately our iron and steel interfaces tend to be below ground a lot of the time. So they've caused us a lot of issues over the years as the insulation flanges have become conductive as they've had moisture ingress, and we've lost all isolation between the steel and the cast iron. We also have isolation fittings on our above ground installations because although we can lose it between iron and steel and other materials, we can also lose our cathodic protection along our instrumentation lines and our any cabling on site, which will then cause us to lose our cathodic protection down the electrical power earth. So one issue we've had is a skills gap or a lack of training. Some of our colleagues have been stripping out isolation fittings without realizing what they were. Some AGIs historically have been designed without any isolation fittings. We've also lost CP through a number of own goals. That picture there shows a water main, which was a fire hydrant ring main on one of our AGIs, which was laid on top of another one of our steel pipelines. Luckily it was decommissioned so we could cut it out and restore the CP on that site. This one is an ironic situation because the yellow pipe is an intermediate pressure pipeline that was laid on top of a medium pressure cast iron pipeline so that we could decommission the medium pressure one. However, straight away the CP was lost, and it took years to locate the touch points and then smash off the cast iron sections that were in contact. That picture there depicts a steel sheet pile driven into the ground adjacent to one of our pipelines, if you can see it in the center of the picture. So other than being a major near miss, that also caused a drain on the cathodic protection. As you can see, when the sheet pile was removed, that's the imprint it left on the pipe. And this is a 24-inch high-pressure pipeline that was constructed back in the British Gas days and laid directly on top of a water main. Luckily, that was another main that was decommissioned, so we could smash it out and restore the CP to the high-pressure pipeline. And that there is where we've removed an old medium pressure pipeline that was in contact with an intermediate pressure pipeline. And you can see the markers left in the middle of the pipe there, where it was in contact and causing a drain on the cathodic protection. And that's thank you. Any questions?
Thank you for your presentation. A really good description for a non-engineer like me of cathodic protection. I was interested, you didn't talk about anything you'd done with other networks, either in terms of researching and benchmarking or sharing afterwards. Can you talk a little bit about that?
Yeah, so the 5 cadent networks, we have a monthly report that comes out from our integrity department that stipulates where we're at and how everyone's performing, as you can see from the graphs I've shown in the picture. So we have had process improvement meetings with the other networks, and originally when we were all using the same contractor, we all had the same issues. However, with the Northwest pulling out, we've showed a drastic improvement using our own contractors and bringing the design back into the Northwest, whereas the other 4 networks have continued to use the same contractor and continue to complain about the same issues. So there is some communication, and we do share best practice.
Lance, can I take you back to the challenge statements that you brought up there? What personal involvement did you get into there with the solutions against them particular challenges?
Yeah, so with the contractor issue, I'd been helping to manage the high and intermediate pressure remediation the year before. So we've been doing the design for the high and intermediate pressure pipelines and issuing it out to contractors within the Northwest Pipelines team for a year, and we'd shown great improvements. When we then had this other contractor imposed on us, and things didn't go so well, I made suggestions that we should employ the same techniques we've been using with the high and intermediate project to then use on the medium and low pressure project. So when it got brought back into the Northwest, myself and my colleague were then responsible for designing, managing, issuing out the work, creating work packs, and following up with any asset data integrity modifications.
Andy?
As I'm not involved with Cadent or even National Grid, I think I go next with the question. You referred to some own goals, and obviously some of those are kind of pretty historic in nature, but the fact that AGIs are being refurbished without insulation joints, can you say a little bit more about that and perhaps what's happened since then in terms of improving knowledge and expertise?
Yeah, so the AGIs were originally designed with earthen systems that did not impact the cathodic protection because they didn't have steel wide armour cabling between the instruments and the above ground pipework. So as these electrical upgrades have been made and steel wide armour cabling has been installed, like you say, there's been a lack of knowledge there from the electrical department, so they've caused drains on the CP from that aspect. So I've been working with a few of our E&I colleagues to try and make them aware of these issues as we go forward, designing new electrical earthing systems on other sites. We've also got capital delivery programs who are doing major modifications on AGIs and rebuilds, and they're liaising with the Cathodic Protection Department from an early stage so that we can inform them of what's required to prevent massive own goals in the future.
Any other question?
Let me answer one then.
Okay,
Go on.
I'm going to go for that.
So, clearly we've gone through a period of non-compliance. Do you have a view of what level of residual risk there is in the network as a consequence of that non-compliance?
Well, if the cathodic protection is functioning effectively, it should halt 99% of the corrosion. So as we've improved on the compliance and brought the schemes back to a compliant level, any corrosion that may have happened should have ceased. We shouldn't have no further corrosion happening on those schemes. We have our annual maintenance and regular surveys to keep track of these schemes. And the schemes that are deemed more high risk that we still have issues with, they're ones that we still have to look at going forward.
A question from the audience then. We've got a minute left that we could have another one. Go on.
I thought it was very thought-provoking talking about removing isolation joints. It sort of made me think, it's a bit tangential, made me think about all the smart meter rollouts and smart meter modules going in, taking out isolation joints that were there to protect the meter modules. In the first place, I assumed, probably wrongly, that it was to stop arcing of street lamps onto services and burning out the regulator. But it does raise the question, when we make changes in industry, what other things are we causing that we don't know about? So it's the Donald Rumsfeld, the known unknowns and the unknown unknowns.
Yeah, we have had instances of CP schemes losing all.
I'm sorry, maybe I haven't phrased that as a question, but...
All right, okay. Well, we have had instances where that's happened, where they've lost all protection as a result of a third party stripping out insulation fittings. And that, although unfortunate, a lot of that we can pick up within the regular monthly maintenance that our technicians carry out. We can see, we have a database that shows the extent of the protection across the network. So we can see every month if a scheme has become non-compliant and then pinpoint, analyse the data and identify the exact location that we're losing the CP from.
Thank you.